Good afternoon, everyone. Welcome to week five live session on structural dynamics. Okay, so in week five, response to the arbitrary motion that's going on live now. There are four modules. Module one, response to unit pulse. Module two is response to arbitrary force. Module three is response to step and ramp forces. And module four discussed about response to rectangular pulse and half sinusoidal wave. Uh, in today's live session, we will be discussing an overview of these four modules, and also in the last live session, we discussed the problems related to forced vibration, free vibrations, free damped vibrations. Okay, so we will be also discussing the problems related to forced vibrations, both free and damped. Okay, so we will start now. So, for example, on our system, a force P of t is acting. P of t is acting, which is varying like this. Okay, some force acts on our system like this. It is having a peak amplitude of P naught, and it's for a duration of T1. It's for a duration of T1. This is plotted P of t from y-axis and its time t. Now, what's the special case here that the duration of this loading, that is T1, is very much smaller than the natural time period of the system T. Okay, natural time T1. So we can call this as an impulsive force. We call this as an impulsive force. Okay. So, what will be the response of our system to these types of impulsive forces? So, impulsive forces in this week five module, you will be looking at these impulsive forces. For example, we have some common and standard impulsive forces, like one will be their step pulse, and one more common studied impulsive force is rectangular pulse. Another one is half sine pulse. This is also rectangular pulse. And another common one is a full sine pulse. You will get to know about all these in couple of minutes. Okay. Uh, so first we will see what impulse is, and later on we will deduce all the relations related to the response of a system to these step pulse, rectangular pulse. Okay. So, for example, we all know this basic concept regarding the impulses. For example, P of t is a dynamic force on our system. Force on our system, on system. Okay. Okay. Then impulse is defined impulse is defined as impulse I is given as integral of 0 to time up to which we have to find the impulse that acts on our system, and it is given as the integral of varying force over time. Okay, P of dt. And for example, we have same like this as I earlier showed, like this time axis. This is force axis. Okay, we have like this. We have impulsive force like this acting. This is P of t. This is t. We have some impulsive force acting like this. Okay, it's having some variation that we don't know. For example, we are interested in finding the impulse that this force imparts from time, for example, this will be reference time 0 to time t1. Okay. So impulse by definition is defined as integral over time from 0 to t1 p of t dt. So when you look at this integral here now, so you will be it will be clear to you people that it's actually the area under the graph, force time graph. Okay, impulse is nothing but area under the force time graph. Okay, so it's actually, sorry, it's actually area under p versus t graph. Okay, so what this impulse gives, it actually gives the change in momentum that happens when the force acts. Change in momentum that occurs when dynamic load acts. So it's clear here that everything is changing with time. That's why I'm telling the dynamic load acts on our system. Okay. So for example, we have impulse, or it's actually the area under the force versus time function. Okay. So it's change in the momentum. So the change in the momentum I will be equal to mv naught. Okay. So we can write it as here. For example, we have like this. We have a shape, some shape like this. We have three, four shapes of the impulses. Like for example, we have rectangular pulse. So we are having one like this. We are having three things like this. First is rectangular pulse. Okay. First is rectangular pulse. We have rectangular pulse. Okay. Pulse like this. This we call as rectangular pulse. We have half sine pulse like this. Sine wave of half cycle. Okay. We have and we have another. Okay, like this. One, two. Okay, we have three types of commonly studied pulses like this. All these are time axes. Okay, and it's force P of t, P of t, P of t, P of t. Okay, so if you assume that the peak of every all these three pulses is same, so for this the peak force is P naught. This for this also the sine graph attains the peak value of P naught, and here triangular pulse, that's the apex, attains the value of P naught. So all these pulses will be having different areas. For example, if we and all these pulses are having same time duration t1 up to t1 and up to duration t1. So if you find the area of each pulse, we will get this will be p naught t1. Okay, area every here area will be uh, 2 by pi p naught t1. Okay, you can find it with integration integral of sine omega t from 0 to t1. It will be 2 by pi p naught t1. Fact, it will be integral of p naught sine omega t dt up to 0 to t1. Okay, it will give this value. Okay, when you find it out. And here the area will be, it's very easy here, 1 half a base into altitude. One base is t1 and it's p naught t1. Okay, 1 half p naught t1. So we can write all these areas in a generalized form. We can write area of any pulse. Okay, let me write it here. We can write in a generalized form. We people can write that area area is equal to alpha times P naught T1, where alpha can take different values depending upon whether it is a rectangular pulse, whether it is a half sine pulse, whether it is a triangular pulse. Okay, so alpha can take the values equals alpha equals 1, alpha equals 2 by pi, and alpha equals 1 by 2. Okay, the people can correlate it with all these shapes. I can make shapes in front of them for your convenience. So alpha equals 1 for this rectangular. It's for half sine pulse. Okay, and it is triangular half. Okay, it's very easy for you people. So I can write. I showed all this because I need it here at this place. Okay, so wait a second. Someone joined. So we can write I is equal to mv naught, and I is actually area, and I wrote it as alpha p naught t1. Okay, alpha times p naught t1 is equal to mv naught. Okay, v naught is equal to, so initial velocity is equal to alpha p naught t1 upon m. Okay, can clearly write this. So taking this equation here. So let's consider for timing undamped free single degree of freedom system. Considering undamped single degree of freedom system. Okay. So for a single degree of freedom system, we have, for example, we have x of t is given as uh, x max or amplitude sine omega t. Okay, something like that. So its velocity will be given as x dot of t will be given as x max, not omega here, we will keep p because we have been studying this with our notations. P as a natural frequency. Okay, x max p cos omega t. Okay, so we can get v naught max here, can write here as x max is equal to v naught by p. Okay, so for v naught we can write from here equation alpha p naught t1 by m, alpha p naught t1 upon mp. Okay, so if we do one thing, we will rearrange the terms. Alpha p naught by, we will divide by k and multiply by k also. K, the stiffness of the system, k by m, and we have t1 by p, t1 by p. So alpha p naught by k is the static deflection of the system. Okay, maximum static deflection. Okay, p naught by k, k by m will be p square t1 by p. Okay, so if we cancel out these terms, so the maximum dynamic response that our system will show is equal to alpha times, that's the factor, x static naught times pt1. Okay, so you people can clearly see that the dynamic maximum dynamic response that a system can show is some uh, term alpha times the static displacement of that system, and that will totally depend upon the natural frequency and the time period of that pulse. Okay, so we can clearly see that the time period of the pulse plays an important role. Time period of pulse, very critical. in determining the response. The max response. Okay, this one thing. So we can see the different types of pulses now. How can we deduce the things for those things? So now we can write here response to simple force pulses. Okay, response to simple force pulses. Okay, so again taking this example, where is it? Okay, this one. For example, we know our governing equation of motion is for example, this time we are having an harmonic external force also, which is exciting our system. So we will have mx double dot plus cx dot plus kx is equal to p of t. This is the force coming from that we are supplying to our systems. So I showed you in the last lecture, when we rearrange the things, we get this. We rearrange c by m like this. Okay, x dot plus k by m, we already know, we replace it with p square. It's the square of the natural frequency of the system, and p of t divided by m. Okay, I will do one smart thing here, that I will divide by k multiplied by k, and m is there already, because m is there here now if I divide everything by m. So in last online session, we replaced c by m as twice theta p. We made this substitution there, and this substitution we already know is given by p square, and this is the thing, p of t divided by k, k by m. So p of t will be also having some variation like that. It will be something uh, p naught some function f of t. Okay, something, because I already told you na here, p naught f of t will be like, if we choose it as uh, f of t will be equal to 1 if it is triangular or something like this, and it will be equal to sine omega t. F of t is sine omega t if it is sinusoidal. Okay, like that. So it also has some variation. P of t will be some maximum amplitude p naught times some function which will be there, either it is rectangular or it is triangular or it's sine pulse. It depends. So it will be here p naught by k. Okay, it will be k by m will be again p square. Okay, p square, and there will be some function f of t that depends upon the type of a pulse. Okay, then we will rewrite this equation. We will get this form that is easy to solve. X double dot plus twice theta p plus p square x, it will be equal to p naught by k. I already mentioned it. P naught by k, it is the maximum amplitude of the external force divided with the stiffness of the system. It gives the x static deflection, maximum static deflection of our system, x static naught, and it is p square is already there, and function, that the time varying function for our for force that is being applied on our systems. Okay, so now when we are going to solve this type of differential equation, okay, so since we have to solve it like this one, it will be it is total solution, that's final solution x of t will be consisting of solution x homogeneous solution, homogeneous solution plus it will be consisting of particular solution. Okay, so homogeneous will be it is thing is when this equation I will write this whole as E, this whole term as E. So homogeneous will be when we will considering E is equal to 0, whole its right hand side is equal to 0 and it is E is equal to something whatever it is there. X static maximum static deflection times P square f of t. Okay, so this will be the particular solution. So we have to find the homogeneous solution as well as that particular integral that we do in the case of differential equations. Okay, so we will be now doing for step pulse first response to step pulse. Response to step pulse. Okay, so we will first take the undamped system. Okay, so for undamped system, taking case of undamped system. Okay, so for our undamped system, we can write the equation like mx double dot plus kx. It is being acted upon by some force p of t, and the variation of this p of t is given like this. We have time axis, we have force axis. Okay, so it is step like initially starting from 0, it is p naught and goes on for whole time constant to be p naught. Okay, it is p of t plotted on y-axis and it's time t. Okay, so here p is called p naught, so I already told you that f of t for this function will be 1. So it's not rectangular here, f of t for it's for step pulse. Okay, step pulse, so f of t is equal to 1. So we can rearrange it like the same way. We can write x double dot plus k by m of x is equal to and again we are writing p of t as p naught f of t. Okay, so we write p of p naught divided by m f of t. Okay, so we can write the terms like x double dot plus p square x is equal to, I'm directly writing it here, p naught by k by m f of t. Okay, okay, it will be x double dot plus p square x is equal to x static maximum static deflection plus p square f of t is 1. Okay, this is our equation. So our equation will be like this. X double dot plus p square of x is equal to p square times x static maximum static deflection. Okay, it's this one. This one. Okay, so we will be solving it since f of t is 1, so its homogeneous solution will be when its right hand side is equal to 0. So if the right hand side would have been equal to 0, so it means that it is free vibrations. Okay, there is no damping, so for free vibrations when there is no damping, we already know the solution. Okay, in the first class we studied the solution for this type of equation, that's x double dot plus p square of x is equal to 0. So x homogeneous will be a cos pt plus b sin pt. Okay, it will be the homogeneous solution and its particular integral x particular integral solution will be equal to x static naught. This just the basic mathematics. We know that x double dot plus p square x is equal to p square x x static naught. Okay, this so it is d square plus p square times x is equal to p square x static naught. I hope everyone is familiar with this type of concepts. Just solving the differential equation. So we write particular integral pi as 1 by d square by plus p square times p square, sorry, x static naught. Okay, so I'm writing it here for your convenience. Pi will be then equal to, if I take p square common, so from the denominator, if I take p square common, p square into 1 plus d square by p square into p square x static of naught. Okay, this one. So it will be shifted to like pi. When we will take the inverse, it will be 1 plus d square by p square whole power minus 1 x static naught. When you will expand this, this will be 1 plus some d square by p square. In fact, it will be minus. By, if I'm correct, it will be minus some higher terms of d square by p square times x static naught. So you see that x static naught is a constant, and multiplying it with the differential d square. Actually, d square, it is d is the term d by dx. Okay, so d square will be obviously d2 by dx square. Okay, so differentiating a constant twice will be zero. So all the higher order terms will give the value zero. So its particular integral pi is, I'm not supposed to give you this much detail because it's just basic mathematics. X static naught. Okay, so we can write the total solution of our problem as x of t will be given as a cos pt plus b sin pt plus x static naught. Okay, this is the solution of our differential equation. So if we are having some initial conditions, for example, for this case, I will take the initial conditions that the initial displacement is equal to 0, initial velocity is equal to 0. Okay, I am taking these two conditions. When you will induce these two conditions into this above equation, we will get our a and b values as a will be equal to minus times x static naught, and b will be equal to 0. And when you will put these a and b values into this equation 1, it will boil down to this simple form: x of t will be equal to x static naught times 1 minus cos pt. Okay, this is the total solution for our problem, in which a system is being acted by a step pulse whose maximum amplitude is p naught. Okay, a simple thing. Okay, we can do the same thing for damped system also, because we considered undamped system. We can do the same thing for damped system also. So for damper systems, we can also do the same thing. If a step pulse acts on our damper system, we can do the same derivation and can extract the response for our system. So I can do that one quickly right here, considering considering the system to be dampened. So we can have the equation there as I already wrote it like here. We can write directly the equation x double dot plus twice theta p x dot plus p square x. I'm just writing the previous equation. P square x is equal to x static naught p square times f of t. Okay. So if this right hand side would have been equal to 0, so this would have been the case of free damped vibrations. So we know for free damped vibrations x of t, that will be the homogeneous solution for this problem. That would have been like this: e to the power minus theta pt a cos p dt a p d times t, okay, plus b sin p dt, okay, where PD is the damper time, this damper frequency of our system. PD is equal to natural frequency times under root of 1 minus theta square. Okay, theta is the damping ratio in our system. Okay, this thing you have to note down. Okay, similarly, since this x static naught p square of t, it's not changing here again, because we already had here uh, here f of t is equal to 1. F of t is equal to 1 for this. So x static naught p square is same thing here. X static naught p square. So the particular integral again here will be xpi will be again here equal to x static times x static naught. Okay. So our total solution for equation in the system in which the damping is also considered, x of t will be equal to e to the power minus theta pt a cos pdt plus b sin pdt plus particular integral pi is x static naught. Okay, this thing, this is the total solution. So if we will be do the same thing, like the initial conditions for my system will be initial conditions are like this one. Initial displacement of system is 0. Initial velocity of system is 0. If I will just put these conditions into this equation, I will get the value of a. I will get the value of a and b like this. First, I will get b as, you have to do the mathematics yourself, mathematical system steps. B will be equal to theta times pa by pd. Okay, this is the value of b, and a will be equal to minus x static naught. Okay, so b will be correspondingly equal to minus x static naught in place of a theta p divided by pd. We can write now p times root under 1 minus theta square. Okay, so p and p will get cancelled, and our b will be finally equal to minus theta x static naught divided by root under 1 minus theta square. Okay, so we can write the total solution for our equation as, after rearranging everything, x of t will be given as e to the power minus theta pt. We have like this one. Mm, a is our minus x static naught cos P dt plus B is minus theta x static naught divided by root under 1 minus theta square, and we have sine P dt, sine P dt. Okay, when we will rearrange all the terms, we will get x of t as x static naught, taking x static naught as common outside, we will have like this one, 1 minus e to the power minus theta pt. We have this one, um, cos p dt plus theta times root under 1 minus theta square sin p dt. Okay, this is the solution we will get for this type of system if we consider the damping also. Okay, this is very simple. We are just considering damping, theta is there. Okay, theta is there. So for example, if theta is not there, we can just plug in theta is equal to 0 here. Anything is for 0 is equal to 1, and here theta is 0. Theta is 0 here, it will be 0, it will be 1 minus cos p, and p will be replaced by pd will be replaced by p here now. So we will get the response as if it was not dampened, like here 1 minus cos pt. Okay, so this thing is there now. We can do the same thing for rectangular pulse. Okay, so rectangular pulse is a little bit interesting one. Okay, first one was response to step pulse, second one is response to rectangular pulse. Second case is response response to a rectangular pulse. Okay, so for example, we have pulse acting like this. We have this pulse. Okay, this one. Okay, like this, and we have rectangular pulse like this, whose maximum value is p naught, and it acts after time t1. Okay, p, sorry, this is time axis. This is time. This is p of t. We can split this rectangular pulse into two step pulses. Very smartly we can do that. We can have like this. First I will take these two. We can do this. Can write this as this one plus this one. Okay. For example, it was acting for time t1. Okay. So I can consider it as a step pulse, some summation of two step pulses, but in this fashion. First step pulse will be starting from like 0, same step pulse, p naught. So it is acting for the whole time up to t is equal to infinity, but I don't require that now. My actual pulse is acting up to time t1 only, and thereafter it is 0. Okay, p of t. So you can see here P of t is equal to P naught for t less than t1, and it is 0 for t greater than t1. But it is here in the first step pulse, it is equal to P naught for whole time duration. And but I can consider one more time after time t1. For example, it is t1. I can consider the same step pulse but in opposite direction of same amplitude P naught but in opposite direction like this. Okay, so I can have composite of minus P naught like here. If I will extend this line, this graph line like this one, so it is having value of minus P naught. Okay, so if I will add these two, first and second, I will actually get the rectangle pulse. Okay, because after time t1, these two pulses will cancel each other and will give the rectangular time, pulse. Okay, time t. So this is one and two. So solution for step pulse one, we can directly write as x of t will be equal to, because we already deduced it, as x static naught 1 minus cos pt. And for 2 we can write, but remember, step pulse 2 is starting after a time duration of t1. Okay, so it is delayed by a time duration t1. Okay, so we have to write all the parameters which are delayed by time t1. X of t, since p naught is same for both things, so x static naught will be same, but here it will change 1 minus cos p. It is delayed by time t1, it will be t minus t1. Okay, the simple thing we have to do here. So total response will be the summation of these two responses. Total response will be x of t will be equal to x static naught 1 minus cos pt, okay, like this one, minus 1 minus cos p of t minus t1. This delayed step also. Okay, sorry, this one. This minus here, it will be minus x static naught, remember, because p naught is negative. Okay, that's why, yeah, I'm saying here we have to do the summation, but I'm actually taking the minus here. It's minus because of x static naught is minus. Okay, total response. So if we will simplify this trigonometric expression, we will get like this one. X static naught cos pt minus t1 minus cos pt. Okay, so for this trigonometric expression cos a minus cos b, we can use cos a minus cos b is equal to minus twice sine a plus b by 2 into sine a minus b by 2. We will be using same expression. So x of t will be equal to x static naught minus twice sine of a is p of t minus t1, b is pt upon 2. Okay, this is one thing. And sine of a is p of t minus t1 minus pt divided by 2. Okay, these two things here. When we will simplify this thing, we will get this one. X of t will be equal to twice x static naught sine pt 1 by 2 upon 2 sine p of t minus t 1 by 2. So this is our response, okay. The response of a system to a rectangular pulse. And we did it very smartly by subtracting one step pulse from another step pulse. And another step pulse was delayed by a time duration of t1. Actually, time duration t1 is the time period of that rectangular pulse. You can see it from 1 and 2. Okay. So we are left with only last one. That is half sine pulse. We will do it quickly and later on we can stop. Case 3. That is third one is half sine pulse. So same thing we are having, like if we will be having this one, same this one, but we are with sine. Okay, okay. We are having this, but these things are not there. Mm, these things. I have to cut this, delete. P note is little bit up and up to time t1. Okay, we are having a sine pulse like this. Okay, we are having sine pulse like this, half sine pulse, and its maximum amplitude is P naught. Okay. So for this thing, we have to find the response. It's acting up to time t1. So our f of t will be equal to f of t. We have to write first thing we have to write f of t. It will be equal to p naught sine omega t for t less than t1, and it will be 0 for t greater than t1. And omega here I am writing as frequency of impulse. Frequency of impulse or frequency of forcing function, whatever you will call. So it is P naught sine omega t force acting on our system. And for this, since it is only half sine pulse, so we can write omega as pi by t1. Okay. So if it was a full sine pulse, it would have been 2 pi by t1. Okay. So our governing differential equation will be, so again we are considering here that damping is not present, and later on we can extend it to the damping systems also. That's very easy because I showed you in the earlier case how we can extend it to the damper systems. So mx double dot plus kx is equal to p naught sine omega t. Okay, this thing we can rearrange the terms and we can write directly it as x double dot k by m will be p square. I'm not writing it here again and again because I showed you p naught by k by m, that will be p square x static naught. Okay, you remember that thing from the earlier cases, x static naught sine omega t. Okay, so you people for know for the homogeneous solution we will have x of t for this thing will be, if the right hand side would have been 0, it would have been the free vibrations, and x of t homogeneous. I'm denoted it by subscript h. It will be a cos pt plus b sin pt. Okay, sin pt. Okay, we got the homogeneous solution. We have to look for the particular integral like this one. Particular integral x of t pi will be, it will be equal to, you have to write it in this notation I earlier showed you, d square plus p square. Okay, it is p square times sin omega t. No, no, not p square, it's p square x static naught times sin omega t. Okay, sin omega t. And you people will be also familiar with this common formula, 1 plus d square plus a square. And if we have a function sine bx in front of it, and we have to apply this operator 1 by d square plus a square. For this we can have the solution like this one. I wrote it a little bit far. We can write it like this. It will be equal to 1 by mm, minus b square plus a square sine bx. Okay, so whatever will be the coefficient of x here, we have to replace d square by the minus of that square. Okay, it's very simple. You have to remember this formula. Okay, so we can write here as, we have the coefficient of in place of we have a variable t here. So coefficient of variable t is omega. So we will be writing it as equal to 1 by minus omega square plus p square. Okay, sine, sorry, we have x static naught p square, and sine omega t will be there again. Okay, if we will take the p square common from the denominator here, we will get p square will get cancelled. We will have 1 upon 1 minus omega by p ka whole square time x static naught sine omega t. Okay, t. So our total solution will be equal to x of t will be equal to a cos pt plus b sin pt plus this one 1 by 1 minus omega by p over whole square x static naught sin omega t. Okay, again my initial conditions first, this is just the equation without giving the boundary condition or the initial condition. Initial conditions here again is, system is initially at rest, so its displacement is equal to 0, so its displaced velocity is equal to 0. When I will use these initial conditions in the above equation, I will get my two constants as a is equal to 0 and b is equal to, you have to carry all these calculations yourself. I'm just writing the final values as minus omega over p uh, x static naught divided by 1 minus 1 minus omega by p or whole square. Okay, this thing. So if I will plug these values in the above equation, I can get finally the value of x of t as x static naught, maximum static deflection of the system, divided by 1 minus omega by p over whole square. Okay, then we have sine omega t minus omega by p sin pt. Okay, this is the final version of the solution. Okay, so this one. We can make the further substitutions like We can have, I already told you, omega is equal to pi by t1, pi by t1, omega equals pi by t1, and our p will be equal to, so pi by t1, and our p will be equal to 2 pi by t. T is the natural time period of our system. So we can write the solution in compact form like this one. When we will use these things, I'm telling to use this here and this here again. Our solution will boil down to x of t will be equal to, it will be equal to x static deflection, and that to its maximum, 1 minus 1 by 4 times time period of the system divided by the time period of the pulse over whole square times, it is sine pi, same ratio, time period of the system divided by time period of the pulse, minus 1 half same time period of the system divided by time period of the pulse, sine 2 pi t by t1, t by t. Okay, this is the final solution we will get. So we covered all the four pulses, three pulses today. That is the step pulse, rectangular pulse, and half sine pulse. For the triangular pulse, we can get the response like the same way. You have to write for triangular pulse like that one. First, I will show here a little bit like, for triangular pulse, we have like this one. So it is like this one. Maybe it will be variation like this, and it's time t1. It will be coming to p naught. Okay, so we have variation of our p of ts. It is varying from 0 to p naught in time t0 to t1 by 2. For example, I am thinking that this triangle path is symmetric, so this is t1 by 2, and it is then again going from p naught to 0 from t1 by 2 to actual t1 time period of this pulse. So easily you can reduce the equation of the motion for the system on which triangular pulse will be acting. So that's all for today. Thank you.